Hi everybody, Mr. Lee here. In this video we're going to go over a charged object being hung by a string, and we're going to introduce a E-field to that charged object so that it deflects. And as you can see in front of you, we have a quick little sketch that I made, and you should also sketch it down. Let's begin. So we have a 2 gram charged object. It's hung in an E-field of magnitude 1,500 newtons per coulomb. So the first thing that I'm going to do, and I think you should too, other than sketch this out, is label your diagram. So we have E is equal to 1,500 newtons per coulomb, and it is horizontal. And it's making a 30-degree angle, and I didn't say if it was with the vertical or horizontal, so I just took the liberty of making it with the vertical. And the question is asking, what is the sign of the charged object? Okay, so with these problems, there's a lot that is within the problem that's not being said. One, for example, is that we are under the influence of the gravitational field. Yes, it doesn't say it, but this problem can't really exist if we're not under the influence of the gravitational field. So what I'm going to do is I'm going to go ahead and I'm going to put in my gravitational field. Let's do it in this nice, beautiful color here. All right. So we are under the influence of the gravitational field. Okay, it's very important to know. I'm going to erase this one here. It's going to mess up my things. Okay, so with that being said, let's actually start off and let's try to solve this problem. So let's think about this. One of the first things that we should always do, if applicable, is try to draw a free body diagram. And in this case, a free body diagram is definitely applicable. So let's go on over here. This dot will represent my ball. We have a string that is pulling up and to the right, and we're going to call that force the tension. Reduce this pen. Because we're under the influence of the force of gravity, or the field of gravity, we're going to call that Fg, because it does in fact have a weight. And this object is being deflected. It's being deflected to the left, but the E field is going to the right. All right, now here's a couple of things that we need to keep in mind as we solve these problems. If we remember from the notes, the direction of E field, okay, shows the direction a positive charge would move. Okay, now this charge isn't being deflected to the right, but it's being deflected to the left. So that must mean that this charge is in fact negative. So we have a negative charge there. Okay, and the reason that we know that it's negative, one thing to keep in mind is as we take a look at these fields, remember the fields, it goes from, the arrows stem from positive, and the arrowhead goes to the negative. Okay, so if this charged object is going towards the positive side, that must mean that this charge is negatively charged, because opposites attract. Okay, so not only that, but we can also say that there is a force, a electric force, that is pulling this object to the left. Okay, now that is a free body diagram. There's also a couple of things that I want to highlight here, and as you solve these problems, trust me when I say it really does help to jot these things down as a way to keep these ideas in mind. One of them is that we are at rest. Okay, so we're not moving, and not only are we not moving, not only are we at rest, but we are at equilibrium. How do we know this? Well, because that's the scenario, right? The problem doesn't tell us that anything else is happening. It's just being hung there. It's motionless. That means that we are at rest. Your velocity is 0. Your acceleration is also going to be 0 because there's no change in velocity. So we're at equilibrium. And this term here, if you remember from the mechanics course, is very, very important. Equilibrium means that our net forces will always have to add up to 0. And that is the key to solving these problems. All right. Now we have all the info out of the way. We have all the important info. I'm going to highlight that because that's also important. We have a free body diagram. We actually figured out one part of the problem. We figured out that the charge is negatively charged. Okay, so now all we have to do is figure out the magnitude of this charged object. So let's begin. With the free body diagram out of the way, what we always did after we created a free body diagram is we created net force formulas. So I'm going to do that next. I'm going to create a net force formula for the x and the y. Okay, but before I do that, I wanna make a very important distinction here. I want to draw another free body diagram, but this time I'm going to add components. Now the reason why I'm saying this is on your FRQs, okay, for free body diagrams we cannot have components. We can only have real forces. Components aren't real forces, they're parts of the forces. And so I want us to get into the habit of not only creating a free body diagram, but on a separate image, a more useful image in my opinion, we're going to draw the free body diagram with the components. And the reason why I say it's the more useful image is because the components help us solve for our problems. All right, so the component that I'm going to create is for this tension because it's at an angle. So let's call this Tx. I'm going to call this Ty. Okay. Now with this diagram, you can add everything and anything that you want to help you solve this problem. So one thing that I want to add is the angle. The problem says that this is the 30-degree angle, and this of course is the right angle. So this must be the 60-degree angle. All right. Now with this, let's identify how we can label these forces. We can say that Fg is equal to mg. We can say Fe is equal to EQ, and we don't have a formula for tension, but we can say that this Ty, I'm going to focus on this angle here because that was our given angle. This Ty is adjacent, okay, it's adjacent to this side here. Okay, that angle is touching that side, and because it's adjacent, it's a cosine. So it'll be T cosine of the angle. It is the y component. And therefore, that makes this T sine of the angle. And why is it sine? Well, because it's opposite. And let me show you what I mean by that. This side here isn't touching the angle at all. In fact, it is across from it. So it's the opposite. So that's Tx is equal to T sine theta, and Ty is T cosine theta. And keep in mind that our theta is 30 degrees. That's going to be a reference angle. Okay, so now that we have our very useful image, let's come up with our net force formulas. The first one, let's do for y. So net force y is equal to 0. Why? Because we're in equilibrium. And I'm going to add up all of my vertical forces. So I have Ty, I have Fg, and those are all my vertical forces. The next line down, so this is just a setup, but the next line down, what I want to do is I want to actually substitute in the formulas. So Ty is equal to T cosine theta, and Fg is equal to minus mg. And the reason why I'm putting it as minus, I should have done it up here, is because it's pointing downwards. All right, so we can say, if we do some fancy manipulation, mg is in fact equal to T cosine of theta. All right, so I'm gonna leave it there because I don't know what we can really do with that, but that's just a good place to leave it. All right, x, we have net force in the x direction is equal to 0, and the reason why it's 0 is because we're in equilibrium. We have Fe, but it's pointing to the left, so let's make that negative Fe, and we have positive Tx, and those are all of our horizontal forces. Same thing, I'm going to substitute in my formulas. So we have 0 is equal to negative E times Q plus Tx, which is T sine of theta. I'm going to rearrange it so we get EQ is equal to T sine theta. All right, now the question is, what is the magnitude of the charge? And if we take a look at our two formula, let's identify what variable we are solving for. So a lot of physics is just setting up the problem so that we can solve for it. This Q right there is what we're solving for. And so what I'm going to do is I'm going to rearrange the formula so that I'm solving it in terms of Q. This is a good habit to get into, especially for the FRQs, where they ask you to derive a formula in terms of the unknown variable. So we have T sine theta divided by E. Okay, now I just want to make a note of the things that we have in terms of value. We don't have T for tension, or the magnitude of tension, but we do have sine of theta, and our theta is 30 degrees, and sine of 30 is 1/2. Okay, so we have this, and this E It's given to us. So the only thing that we don't have is this t. But luckily, over here, we have tension. So I'm going to rearrange this. So we have t is equal to mg divided by the cosine of theta. Okay? Now, at this point, what we can do is we can just substitute in what we just found over here for tension into this formula over there. So we get Q, oops, let's undo. All right, so we get charge is equal to mg sine theta, cosine theta times E, all divided by E. All right. So if the problem was looking for you to solve it in variable form and variable form only, this will be it. In fact, we can clean this up, right? Y'all see this? So we get Q is equal to mg sine divided by cosine is just simply tangent of theta divided by E. And all we have to do at this point is plug in our values. So this would be a great acceptable answer, but if we wanted to find a numerical answer, we can say that M, what was our mass? 2 grams. Okay, so our mass was 2 grams, so that is 0.002 kilograms times g. We're going to use 10 for the acceleration due to gravity. Tangent of 30, divided by 1,500 Newton coulombs, and we're going to plug that into our brain calculators and get 7.54 times 10 to the -6, I believe. -6 coulombs. Always have your units. If you're wondering, Mr. Lee, how did you do that in your brain? Well, it takes years of practice. But trust me, when you do enough of these, you'll get used to using your brain for these types of calculations. All right. So that is the magnitude. But if we want a official answer, we can say that Q is equal to negative 7.54 times 10 to the -6 coulombs. Booyakasha. Final answer. Okay, and that is how you solve for a charged particle being hung by a string in a E field and a G field. I'll see you next time. Bye-bye.